So today we're going to start in with acid and bases, and this is going to be one of the more important topics on the AP exam. And so the first thing we need to do is we need to define what acid and bases are. So let's jump right in here. And one of the things that you're not going to like almost from the very beginning is that there are multiple ways to define acids. So I'm going to define these three, and I'm going to tell you which ones we have to really focus on here. And the first way we define acids is by a guy by the name of Arrhenius, and he said that acids produce hydrogen ions and bases produce hydroxide ions. Now, this is important because as you take a look here, this part here where it's in aqueous solutions, it means this. Arrhenius said that acids are things that when you throw them into water, this is H2 over here, they produce H plus ions. And when you throw a base into water, it produces OH minus ions. This is a pretty specific definition for acids. So an acid has to have an H plus that when you throw it into water will produce H pluses, and a base, when you throw it into water, will produce OH minuses. Now, Bronsted-Lowry had a little bit more of a vague definition, and he said this. Acids are proton donors, and bases are proton acceptors. Now, what does that mean? That means simply this. An H plus is a proton. So somewhere in your notes here, just write this. H plus equals a proton. And we're going to talk about that in just a second why that is. But what essentially means is that acids give up H pluses and bases take them. And the last definition, which, by the way, you'll note here, is no longer on the assessed in the AP exam, but actually matters to us just to understand conceptually what's going on, is this, that acids are electron pair acceptors and bases are electron pair donors. Keep these definitions kind of around as we go through this, but I want to talk to you specifically about a couple of things here that you probably already make sense to you, but I want to specifically tell you what the difference is between a regular hydrogen and a hydrogen ion. Now, this is not going to come in as any surprise to you here, but hydrogen, a regular old hydrogen, it is just has one proton and it has one electron. Now, if you take a look at a hydrogen ion, that's one that has lost an electron. So if you take a look at it, why do we say that a hydrogen ion is a proton? Well, because that's all it is. It has no electrons at all. In both cases, the most common form of hydrogen doesn't have any neutrons, so that's neither here nor there. But the electron configuration, I mean, it's kind of fun here. It's 1s1 for regular hydrogen. It's 1s0 for the hydrogen ion. Now, the other thing to be aware of is this. When you have a regular hydrogen, it has an electron in its orbital. In a hydrogen ion, there are none. And that's going to be important because if there are no electrons in that orbital, then that orbital can accept stuff that normally it wouldn't be able to accept. So, two things to make note of. The hydrogen ion is only a proton, and the 1s orbital has the ability to hold two electrons. And since it's empty, the H plus ion has the ability to accept a pair of electrons. So it can actually take two electrons in this orbital because it makes sense. There are two spots here that it can accept electrons. And normally whenever you're forming a covalent bond, you have one atom give an electron, another atom give an electron, and they share. But there's a different type of bond, which we're going to talk about right now. Now, before I go any farther here, this right here, H plus is the same thing as H3O plus, is a staple. We use those interchangeably all the time. But if you take a look at that, you're like, wait a second, H plus is not H3O plus. Well, remember I told you this a little bit before, but every single time we're dealing with acids, every time we're throwing it into water. And whenever we throw something into water, the water gets a chance to interact with them. So H plus is essentially water interacting with it and grabbing on that hydrogen and including it as part of itself. Now, how does that happen? Well, we say that the H plus is connected to a water molecule by a coordinate covalent bond. What that is when one species, and in this case it's going to be water, donates a pair of electrons to form a bond. So it's really the best kind of sharing if you're receiving. Can you imagine if you're like, hey, your sibling has 2 chocolates, and you're like, hey, share those with me, and you get both the chocolates? I mean, that's the greatest time. You don't have to like try and barter back and forth, you giving them a licorice stick, because who wants licorice, right? Those of you who like licorice, I await your emails. But the best kind of sharing, if you're a receiver, is coordinate covalent sharing, because one atom or one species gives both. Now, there are two examples I want to show you here. Take a look at hydroxide and ammonia. Both of these have pairs of electrons that they can donate. I want to point out another example to you here because it's really relevant. Let's take a look at water. You see how water has these pairs of electrons that it can actually share as well? And because they have these free electrons, they are free to form a coordinate covalent bond. Now I'm going to come back here in just a second and show you how this works. But let me take an example of boron trifluoride. This is an example of a Lewis acid. Now I said that we're not going to cover Lewis acids and bases because they're not needed to be defined, but I want to show you how this works so you understand what H3O plus or the hydronium ion actually is. So if we were to take a look at BF3 and we were to put them together, now this right here, this is a poor man's version of an sp2 hybrid, because if we were to actually do this, aren't there one s orbital and two p orbitals, aren't they going to come together to form three, this is going back to our old school roots here, three different sp2 hybrid orbitals. Now if you're like, oh crap, I don't remember that stuff, you might want to look back and at the chapter 9 in the textbook, and there's going to be one p orbital that is, and this is a 2p orbital, that has nothing in it. So these are all in the second energy level. I'm not going to put a 2 in there, it's going to make it ugly. But essentially what you have is you have the first three hybrid orbitals that are being shared between the boron and the fluorine. Now, if you're like, wait, I don't remember how this all works. Remember, this central atom, however many things get thrown into the blender, that's how many orbitals you have. And since the boron has an s orbital and three p orbitals, it throws three of them in there to form the bonds with the three fluorines. Again, look back into the chapter 9 stuff if you're having a little bit of trouble with this. That leaves this orbital right here completely empty. And what does that allow for? It allows for other things to donate 2 electrons, forming a coordinate covalent bond. This is the exact same thing that hydrogen has the opportunity to do. So if you take a look at hydrogen, right? Hydrogen has an open, well, I don't know why I put a hydrogen under there. Let's pretend that I know what I'm doing as a teacher, yeah? If I look at this 1s orbital right here, it is completely free. So if I take a look at water, right? Water has, if remember, and I'm just going to do this in the easiest way possible. I'm just going to do it like this. Doesn't water have 2 extra pairs of electrons on here? And so what can happen is that pair of electrons can get donated here to be shared. And what ends up happening is that when those electrons get shared onto here, what you end up with is a molecule that has an extra electron, an extra hydrogen on it, and it looks like this. This is the hydronium ion, and it is essentially the same thing as H+. Now again, this seems a little bit weird to you, but I remember one of the hardest things for me when I was learning all about acids and bases is that the professor would talk about hydrogen ions and then he referred to them as protons. I'm like, what the heck? How is a proton the same thing as an H+? That's because H+ is essentially just a naked proton. The other thing he started talking about was how the hydronium ion is being released, and and he kept on going back and forth between the hydrogen ion and the hydronium ion, and I didn't understand what that meant. What that essentially simply is saying is this. The hydronium ion is a water molecule that is added onto it, an H+. And the way it does that is with something called a coordinate covalent bond, which is where the water molecule very generously donates both of one pair of electrons to the H+, and in that way it forms a bond holding on to it. And so these two things are going to be used interchangeably because every time we deal with H+, when we throw it into water, it forms hydronium. Those H+ that are wandering in water, that's what it does. Now, that's going to be in our next video where we talk about what the heck is going on in water. There's a lot of stuff. So hopefully this has been helpful as an intro, and we're going to hit it hard with the next video as well. Have a blessed day.